Hello and welcome to the course on optical communications. In this module, we will continue the discussion of the previous module. We will apply the steps that we outlined in the previous module to discuss and derive the optical modes inside an optical fiber. Okay. We have spelled out all the assumptions in the previous module, so please go back and refer to those assumptions. So the objective in the previous module, at the end of the previous module, was that we were about to calculate the electric field and the magnetic field pattern, and we would be starting with step 1, which corresponds to having starting and noting down the Maxwell's equations in the appropriate coordinate system. Because this is like an optical fiber which is cylindrical in nature, it is easy for me to talk about the easy for me to consider the cylindrical coordinate system. Cylindrical coordinate system is characterized by r, phi and z coordinates and the unit vectors along r, phi and z. In terms of those, the curl equation is given by this particular expression. So you don't have to remember this, you can look at it from any textbook or any handbook of mathematics. The curl of h, I have used h in this example, but you know that E also needs a curl equation. So in that case substitute h with E. Okay. So curl of h has 3 components, r, phi and z components, and for your bad luck none of these hz, h phi or hr components are 0. So everything exists, so welcome to complications. Simple way of remembering this, if you are keen on remembering this, is to think of this as the determinant, which is given by r hat by r, phi hat and z hat, where r hat is the unit vector along the radial direction, phi hat is the unit vector along the azimuthal direction, and z is the radial, z hat is a unit vector along the z axis, that is axis of the cylinder. So you have those r hat, phi hat and z hat, and this is the expression. Del by del r stands for the partial derivative of with respect to r, del by del phi is the partial derivative with respect to phi, and del by del z is the partial derivative with respect to z. So this is the curl of h. Step 1, write down Maxwell's equations. So I have written down curl of h having all these components, but I know that curl of h on the right hand side is given by j plus del d by del t, or because time derivatives have been thrown out by converting into the phasor form, del by del t becomes j omega. So this becomes j omega into d. Luckily for us, j will be equal to 0 because there is no current inside an optical fiber, because optical fiber is made out of dielectric region. So the dielectric, we are assuming it to be perfect dielectric, no losses in the dielectric, therefore this term will be equal to 0. So lucky for us, j is not there, but you still have j omega d. There is one further simplification that you can make with this equation. You can say that this is j omega epsilon E, and the value of epsilon will be different for the core and it would be different for the clad. So this is for the core and this is for the clad, where epsilon 1 and epsilon 2 are the relative permittivities. But I also know that relative permittivity is nothing but refractive index square. So I can write down this epsilon as epsilon 0 n square. I will substitute n is equal to n1 for the core region, n is equal to n2 for the cladding region. Okay. So anyway, we will not make this substitution at this point, but I just said that you can do this one slightly later. We will do that one slightly later. So I have on the left hand side of this expression given this complicated looking expression, but the right hand side is j omega epsilon E. But if you have to expand this E itself, E will be r E r plus phi E phi plus z E z. So you will actually have E r component, E phi component and E z component, right. Then you can equate the r component on the left hand side, which is this expression, to the r component on the right hand side, which is j omega. So if you multiply this whole thing by j omega epsilon, then j omega epsilon E r must be equal to this expression, okay, the one that I am showing here. So this expression. Similarly, there will be a phi expression, or the component for the phi, that should be equal to j omega epsilon. This should be equal to j omega epsilon E phi hat of course, right, because it is the vector equivalence, and this last one should be equal to j omega epsilon E z. Okay. Again epsilon should be different for core and cladding, that you have to keep in mind. Okay. So, we have written down del cross H equal to this equation, this is called as Ampere-Maxwell law. Then you also have Faraday's law, which is del cross E is equal to minus j omega mu H. I will leave this as an exercise to show. Okay. So, del cross E again will have the same, you know, 3 variables. In place of H you can simply replace E, and you will have to equate this one to the right hand side. In the right hand side you will have minus j omega mu H. Okay. So, let me just write down, it will take some time, but I would like to just write down this one so that you see all the equations at one side. Okay. So, let me just write down these equations. So, equating the R components, I get 1 by R del Ez by del phi minus del E phi by del Z. This should be equal to minus j omega mu into HR. Now, we introduce one more assumption. We will assume that no matter what the electric field or the magnetic field components are, as a function of Z, they are given by e power minus j beta z. They are characterized by a certain propagation constant e power minus j beta z. Therefore, when you take del by del z here, right, on the z dependence, what you are doing is you are simply pulling out this minus j beta. Just as for the phasor e power j omega t, you took del by del t and pulled out j omega, here you are pulling out minus j beta. So, in the place of this minus del E phi by del z, I can write minus j beta times E phi. So, this part can be rewritten. So, I can rewrite this equation, I will write down here in the blue, maybe just to show the difference. You get del Ez by del phi plus j beta E phi, this whole thing is equal to minus j omega mu HR. We do this simplification in other places as well. So, the next equation that I get will be the phi term, which is j beta ER plus del Ez by del R should be equal to j omega mu H phi. Okay. And then you have the third equation, which is the Z component. You get 1 by R del by del R, R E phi minus del ER by del phi. This should be equal to minus j omega mu Hz. You are not lucky enough to replace del Ez by del R or del Ez by del phi. Well, that is the life, you know, you do not get everything that you want. So, these are the curl equations for the electric field or the Faraday's law. There must be equivalent or there must be analogous equations for del cross H as well, which are anyway obtained from the top one, right. So, what I will do is, I will also leave this as an exercise to write down the corresponding terms to the H, del cross H equal to J, del D by del T term. I will start off with one expression, you can fill in the remaining two. So, you will have 1 by R del H Z by del phi plus J beta H phi, right. So, replacing E by H, this should be equal to j omega epsilon E R. So, you can fill in these two. What you do in the next step is that you need to express ER, E phi, HR, H phi in terms of Ez and Hz. How do I do that? Well, I have to try and, you know, equate couple of these equations, right. For example, if I look at this one, I know that ER is given here. So, if I look at this equation, to the left hand side I have j beta ER, there is del Ez by del R, right, and then j omega mu H phi. There is also one more equation here, which is j omega epsilon ER equation, which involves a j phi term here and a Hz term here. So, if I can combine these two equations and substitute one in place of the other and simplify them, then maybe I will be able to obtain a relationship for ER. Okay. So, I mean, I can try doing this, you can eliminate one with respect to the other. So, if I will just try it out now to see whether I can still do this analysis. Otherwise, as usual, I will leave this as an exercise to you. It is not complicated, you just have to look at one equation, substitute for the other. Okay. So, let us substitute for H phi from this equation, right. So, from this equation let us substitute for H phi. Let me rewrite that equation. So, I get j beta H phi is equal to j omega epsilon r E r minus del Hz by del phi. So, I can substitute for H phi in this expression, right. So, in this expression I can substitute. So, I get j beta E r plus del E z by del r is equal to j omega mu. For H phi I can substitute j omega epsilon r E r minus del Hz by del phi. Okay. So, if you expand this out, you get minus omega square mu epsilon, there is r E r, right, and then you have minus j omega mu del Hz by del phi. I can pull this E r onto the left hand side. So, I get j beta plus omega square mu epsilon. Okay. There is an r E r here. I hope that I have got the r E r components correctly. So, I do get r, this whole thing times E r must be equal to minus j omega mu del Hz by del phi. There is also minus del Ez by del r. Okay. So, you get minus del Ez by del r. If I take minus j as a common factor, or no, maybe I do not want to take them as a common factor at this point, but I can write down this E r as minus j omega mu del Hz by del phi minus del Ez by del r, this whole thing. So, minus I can take out as a common factor. So, this becomes plus inside the brackets. So, there is a minus sign sitting out, divided by j beta plus omega square mu epsilon r. There seems to be a small problem here because I am not expecting this r here. So, I was not really expecting this one. In that case, maybe where I have made a mistake is to write down the simplification somewhere. So, you can actually go back to this equation. There was j omega epsilon times E r here, and there was a 1 by r term sitting there, and this was del Hz by del phi plus j beta del H phi. So, maybe when we substituted this equation, we got j beta H phi is equal to j omega epsilon r E r minus del Hz by del phi. So, we can look at that equation, and then maybe you will forgive me for this one. What I would like to give you is the final expression. So, and I would like to give this as an exercise to you. The result for E r in terms of Ez and Hz is that you get minus j by q square, there is beta del Ez by del r plus omega mu by r del Hz by del phi, where q square is nothing but, or q square is given by omega square mu epsilon minus beta square. Okay. And we know that omega square mu epsilon defines the propagation constant k square. So, this can be written as k square minus beta square. Obviously, in the core region k is equal to k1, because this is nothing but the free space wavelength k0 times n1, right. Whereas, in the clad region k is equal to k2, which is k0 times n2, and clearly k1 is larger than k2 because n2 is smaller than n1. Okay. So, these are some results that you will know, and if you look at the way q should behave, q would actually be positive in the core region and q square would be negative in the clad region. Because of this, there will be an oscillatory solution here, and because of this nature there would be an exponentially decaying solution, as we will see later. Okay. So, this is just for E r, where again I think I have made a mistake in multiplying the terms somewhere, you can just figure it out where I have made a mistake. That might be a very good exercise for you. So I will leave this as an exercise to show that ER is given by this. Similarly, you can look up the textbook and find out expressions for E phi in terms of these components. So I will give you the answer, you can sit and verify this. Okay. So this would be beta by R del Ez by del phi minus omega mu del Hz by del R. Similarly, there will be HR and H phi. I am not going to write them. You can look at the textbook, right, which is the textbook that we are following for the course, and this is page number 53 of the 5th edition. So all these formulas are taken from there. So you can look at the textbook when you have some time. Okay, this completes our step 2. But what about step 3? Well, I need to know what is the step 3. Step 3 comes from solving Helmholtz equation, that is del square plus k square into Ez or Hz equal to 0, except that you now need to write down this del square in the cylindrical coordinate system, okay, which again is a little bit of a problem. So you will have to get to the expressions for the cylindrical coordinate system. I will just give you the solution here. Okay. Since we are applying del square to Ez, and in this particular case it is not k square which needs to be evaluated, I mean included, but rather q square, because that would correspond to omega square mu epsilon minus beta square. Okay. So because of that, this would be q square. Okay. In the case when you are assuming that Ez goes as e power minus j beta z. Okay. So alright, let me just prove this one. If you are a little bit confused, I can prove this one. So let me write down what is del square applied to Ez in the cylindrical coordinate system. So del square applied to Ez in the cylindrical coordinate system is another complicated expression, but this is 1 by r del by del r r E z. So this is actually r E z by del r. So this is the r expression plus 1 by r square del square Ez by del phi square plus del square Ez by del z square. So this is the expression for del square. Now to this, if you add k square Ez, I can add k square Ez, and I know that del square by del z square is nothing but minus j beta whole square, because del by del z pulls out minus j beta, again you pull out minus j beta, minus and minus is plus, so j into j is minus, so this is actually minus beta square, right. So to this, if you add k square Ez, what you get is, when you group the terms for kz, you are going to get k square minus beta square into Ez. The dependence on r and phi still remains the same. So this plus this equation, and this is the reason why I said k square minus beta square, because that is defined as q square. I can replace this into this expression. Okay. So if I do this and then write down what is the resulting expression, also after taking this double differential thing, after differentiating this one partially with respect to r twice and simplifying this equation, you get del square Ez by del r square plus 1 by r del Ez by del r plus 1 by r square del square Ez by del phi square plus q square Ez is equal to 0, and you will get a similar expression for Hz as well. So similar for Hz component. So this is the complicated equation that you are about to solve. However, the solution can be written in the form of well-known functions if I recognize that phi is actually a periodic function, right. My solution should be periodic in phi, because if I change the azimuthal angle from say some value phi 0 to phi 0 plus 2n pi, where n is an integer, I should basically get back to the same point, right. It is like going around the circle and I am back onto the same point when I change this n into an by change the angle by a 2 pi radian thing. So my solutions also should be periodic. They have to reflect this periodicity around the cylinder when you go in the azimuthal direction. So that kind of a constraint allows us to choose the solutions as some e to the power j So let me choose this one as some new phi, okay, where new is an integer, okay, new is an integer. So my solutions in terms of phi will be along e to the power j new phi, okay. My solutions in terms of z, I know they are of the form e power minus j beta z. The only thing which I do not know is what is the solution along r. Substitute this kind of a solution into this expression. So when you take del square by del phi square, this e to the power j nu phi will pull out j nu whole square, right, which is nothing but minus nu square. So I can go back and rewrite the expression, the wave equation here. I can say del square Ez by del r square plus 1 by r del Ez by del r minus nu square by r square plus q square times Ez is equal to 0. So this is all Ez, so this is plus, so you get a slightly simplified equation, okay. And since this is only r, function of r, because for a new constant value of nu, this entire term q square minus nu square by r square is just a function of r. So I can remove this del square by del kind of a thing and go to total derivative. So I get d square Ez divided by dr square plus 1 by r dEz by dr plus q square minus nu square by r square into Ez is equal to 0. It turns out that the solution of this equation is known as Bessel equation, Bessel differential equation. The solutions of this are of two kinds. This is the first kind, and there are two types of first kind solutions which are given as j and let us say some, this one that you need. So this is nu is the integer here, j nu of some argument. So if I call this argument as u square inside the core and w square in the cladding. So u square is the core and w square in the cladding. The solutions will be of the form j nu of ur, and then there will be one more solution which is n nu of ur, okay, for the core solutions. And because in the cladding region this is defined as, rather I should define this as minus w square, because I would like to define, I am anticipating the result that the solutions have to decay. For the solutions to decay out inside the cladding, this argument q square minus nu square by r square should be negative, okay. So that is given by negative w square, okay. So because of that I get the solutions of the second kind. The second kind solutions are y nu of wr and let us say k nu of wr, okay. And if you look at how these equations behave, you will see that if you sketch them as a function of the radial distance, this is how the solutions would behave. This is your j0 of some r, this is your j1, then you have j2, okay. These are like damped sinusoidal excitations. And then if you look at n, that is the cell function of the first kind, but with n, you will see that these are all going towards infinity, or rather minus infinity at r equal to 0. Then the other solutions, namely y and k, the solutions for y will go as exponentially decaying solutions. So these are the solutions, and then for k you have exponentially increasing solutions, okay. Based on this nature, it is obvious that if I want some guiding inside, I have to choose these as the core modes and I have to choose these as the clad modes and reject these, because at r equal to 0 I do not want my field quantity to go to infinity. Similarly, my field quantities outside the cladding are not going to increase exponentially, rather they would actually decay exponentially. So because of that reason, we will choose in the core region oscillatory solutions, in the clad region exponentially decaying solutions, okay. So my expression for Ez will be, after solving for r less than a, that is to say in the core will be given by some constant a, okay. Similarly, Hz for r less than a, that is inside the core region, so this entire thing corresponds to core region, will be another constant b. In terms of their behavior inside the core, they have to be Bessel function of order nu, first kind Bessel functions order nu, and the argument for that inside will be ur, and there will be e to the power j nu phi, nu is the integer, e to the power minus j beta z, okay. For the clad mode solutions, the solutions must be for Ez r greater than A and Hz r greater than A. These have to be some constant C and D. The constant C goes for Ez, constant D goes for Hz. The argument here will be the same. It would be y nu of Wr, because these are the ones which have to be decaying, e to the power j nu phi, e to the power minus j beta z. Okay, so these are the constants A, B and C, D which you need to determine. One very important thing before we end this module is that the value of u, which is k1 square minus beta square, that is given by k0 square n1 square minus beta square, has to be positive, which means that k0 n1 is greater than beta. W square, which is defined as beta square minus k2 square or beta square minus k0 square n2 square, has to be positive, or rather the k2 square minus beta square has to be negative, or W square has to be positive. Okay, so that is the solution. So for this reason k0 n2 should be less than beta. So you will see that you actually end up with a range of values for beta. On the lower side you have k0 n2, on the upper side you have k0 n1, and the value of beta will be any discrete fellow that would be lying between k0 n2 and k0 n1. Okay, you can actually substitute, apply boundary condition. Okay, I will not talk about the boundary conditions here. The boundary conditions are for the tangential components at the boundary interface r equal to a, that is Ez and E phi. Please remember, Er is not the tangential component at r equal to a. Similarly, you have the tangential component Hz and H phi for the magnetic fields, and all you are saying is that these values in the core must be equal to these values, that is to say the values Ez in the core and E phi in the core must be equal to Ez and E phi in the clad. I already have Ez, but then it is your job to find out E phi. Okay, what is E phi? Find out that. Similarly, there will be an equivalent results for Hz and H phi as well. The core Hz and H phi must be equal to clad Hz and H phi at the boundary. Okay, so you can apply the boundary conditions and you will end up with a complicated equation for finding beta. That equation is called as the characteristic equation, which gives you the roots of beta. Also, if you solve the characteristic equation, you are going to find the values of beta. In the next module, we will take up mode properties. Thank you very much.